This conference will now be recorded.
Okay, so hi everyone. Thanks for starting the recording. Here's the agenda for today. This is the 10th meeting of TAP. And we'll start with a few updates before we go into the presentation by Kevin. So let's start with the updates since last time we met. So last week we had a very successful OCP Tech Week. On November 12th, on Thursday, we presented the vision, the mission statement, the work streams, and we pretty much went into all the gory details in order to enable the community, enable the vendors and partners and operators to participate in this exploration and in building data center appliances. So I think we had a very good turnout and a lot of feedback. In fact, a lot of echo is still happening with around this event, and we're very happy with the turnout and the conversations we were able to engage with. If you have any questions or if you have any further discussions that you want to raise, then please reach out to us or feel free to do it now.
Also, I wanted to add, so we basically published the timing card. So if you want to find it, it's simply just the URL is www.timingcard.com. So you get basically to the GitHub. Everything is there available. And if you want to contribute in the project, just let us know. We add you an invitation. You can add things and have your interpretation of it and so on.
Great. That was a big announcement that came out last week on the Tech Week. It belongs to workstream number 1. So that's the open source Grandmaster. Thank you, Ahmed, for the URL. I just added it here. And what we have now under the workstream number 1, led by Oleg, is that we have not only the spec spelled out, but also the first CAD files for what is a timing card, all published publicly. And we have first vendors coming in with timing cards. So we mentioned during the presentations, both cards by NVIDIA and by Aurelia Facebook that adhere to the specification which is being shaped. And I guess that we'll put the emphasis now on finalizing the specifications and announcing them in an orderly fashion through the OCP so we could have other vendors and operators join this. For workstream number 2, which is the data center PTP profile, we have also shared the concept and the goals. This was done by our colleague Michel. Michel, would you want to speak to that a little bit more in what's coming next from your work?
Yeah, thanks, Elad. So if most of you on the call remember, at the end of September, we basically went through a glimpse of what the data center PTP profile document looked like. Since then, there's been some good progress on the write-up. In 2 weeks from now, which is our next call, we're going to be sharing the first version of it. And at that time, I mean, it's going to be ready for review. I know a couple of people that attend the call have shown interest in participating into the review. The review very likely, we're going to decide maybe it's going to be done using, for instance, like just tracking changes in a Word document, or maybe do it like what is being done in Workstream 1 through GitHub as an example. We haven't fully decided on that. So, and very likely the logistics of this, maybe we'll decide to break out Workstream number 2, for the purpose of reviewing and comment resolution. But all of that is going to be presented and discussed next week. Yeah. So looking forward to that. Yeah.
2 weeks.
Thank you. Back to you, Alan.
Michelle, you mean
Yeah.
in 2 weeks? The next
Yeah,
iteration.
in 2 weeks.
Yeah, so it's a bi-weekly, so next iteration. December 2nd. Thank you so much, Michelle. So before we go and present our speaker and the presentation for today, I would like to open the microphone and see if there are any comments or feedback to the progress we're making here, or suggestions from the audience. Okay. Sounds too quiet, but I'll take it as if we're doing all the right things and we're engaging offline. So for the presentation today, Kevin has been attending our calls. Kevin Stenton from Intel volunteered to be talking about computer timekeeping and synchronization. Kevin, are you ready on your end?
Yeah, I think I just need to get authorized to share my screen.
Yeah, I'll do it right away.
Thank you.
So you're K, how do you spell your name here? Just Kevin or KT?
I don't know how I'm listed.
Okay, found you.
Elad, it's worth to mention also the topic that Kevin is intent to talk about was question. We got a lot of questions during the Tech Week. It's a hot topic, and I think we are looking forward to hear you, Kevin.
Do you want to reiterate the feedback we got on Tech Week?
Yes, people, the crowd asked us, while the NIC clock is so well disciplined and synchronized, what do we do with the system clock? What is the best way to do that?
Thank you. Kevin?
I'm sorry, I was, if that was a question to me, I'm sorry, I was getting my computer set up.
The time was setting the stage for you.
Sorry, yes. Thank you for the introduction, even though I missed it. Hopefully I was the only one. What I'd like to do today is talk about computer timekeeping, in some ways going back to some first principles, also giving a bit of a history of how we got to here, and hopefully have a rich discussion in the remaining 45 minutes of the hour on some of the ideas that should be nothing really new to many of you. And I did recognize quite a few familiar names. So thanks for giving me the opportunity. So I should note that this presentation arose from a presentation I gave, I guess, 11 months ago at the International Symposium of Precision Clock Synchronization, basically the 1588 conference that was held. And really the question as part of the keynote was, what if my local notion of now could be used to unambiguously order events? And I could use timestamps to prove causality, and therefore use synchronization not only to measure or improve overall system performance, but actually to be used in the correctness of algorithms. And there have been examples of this. Many of you, I'm sure, are aware of. But it's a big question, I think, for the industry to think about. How can we provide dependable time with the level of accuracy that would allow us to use it really for the correctness of algorithms? And so just to go really down into the deep technology here, and this will not be a tutorial on PTP or POSIX clocks or anything like that. You've had plenty of really good presentations on some of those in the past. But if I ask in software what time it is now, I can use POSIX clock get time. I get a set of integers. Let's say call them nanoseconds since 1970 nominally. But what does the number mean? With whom is it that time? With respect to whom? What's the accuracy level? What's the level of trust? And when I read the now, how long did that take? And is it still that now? Now, in other words. So that's just to put a little bit of the context. Historically, if we go back, I actually found a very early article in Byte magazine, believe it or not, 1977, on adding a real-time clock to your computer system. And in this case, it's interrupts that are driving a software counter, which keeps time. So it was a symbiosis between hardware and software to keep time, because at the end of the day, time is a property of physics, and we need hardware in order to maintain it. So fast forward, and this is not a product pitch. This I don't know if this product's even available still. This is back in 1993, I think, when the read TSC instruction was introduced. And my first PC was a 90 megahertz Pentium, I think about at this time, and it was really an introduction of a new concept into computer science in some ways, where before algorithms would be correct or incorrect based on the logic, but nothing temporal was really required for the correctness of an algorithm, unless you're talking about some embedded system. And so this instruction allowed an application very quickly to read a counter which ran nominally at the CPU frequency. If you have a 60, 90 megahertz Pentium at the time, it would run at 60 or 90 megahertz. Well, the part of the transition that the industry had to go through was thinking about time for also real-time applications. And one of the examples there was, maybe you remember, the turbo button that you could push in order to slow down the world if you were running a game that was timed for something that was a slower CPU. So fortunately, TSC helped to address this kind of problem and allow a constant time base to be used for applications. And then we went through a phase where power management was added, and there was the challenge of how do we maintain time when we go to sleep, and also just to go through to the multi-core CPUs, where I have an application that could be migrating from one core to another. And of course, it's very bad if you have an operating system that assumes coherent time and discovers that time went backwards, when we know that in practice and in physics, in reality, time only always goes forward. And so time synchronization was then required across multi-core CPUs, where cache coherency, for example, was assumed. So what I'd like to do is just now give a brief introduction to computer timekeeping, at least from my perspective, and some of the all of this is public information, so there's nothing secret here. But one of the ways that this is accomplished today is with really starting with the oscillator. So of course, you can't have timekeeping without something that is oscillating. And computers these days have an oscillator in typically tens of megahertz range that's used for driving the circuitry on the on chip and on the system. And at least for Intel architecture, there's this always running timer, ART, that's defined in the software developer's manual. So I'll show us a picture of a snapshot of that. And that is running at the crystal clock, core crystal clock frequency. It just counts up monotonically. That's multiplied by an integer and divided by an integer, which is also hopefully a power of 2. And then some offsets can be applied per logical CPU. Hopefully those offsets are always 0, because when they're not 0, it can cause issues with the operating system. And then finally, that becomes the counter that that you can then read in an application by executing the user space the read TSC instruction. So what was once a very simple, it's a counter running at the constant 60 megahertz crystal or clock rate of a early Pentium. Now it's a little more complex, but then that allows synchronization across the CPU complex. Okay, any questions about this so far? Take a sip of my coffee.
Yeah, I have a question. Does the so thank you for that. That definitely is, a few things are new here, but I have a question regarding the reading this CPU TSC. Is there a way to read it in different ways, or it's always one single approach to this TSC?
I guess there are multiple ways you can read the value, but typically you just execute the read TSC instruction and it returns the current value in a register.
Normally,
it's also an MSR, so you could read it as an MSR. Also, I'm not completely sure about that, but yeah, go ahead.
Yeah, normally software would like to see the difference. What's the difference between this CPU time and either peripheral time or a different socket time?
Yes.
So is there a way to do it synchronously?
Yeah, we'll get to that. It's a great question.
Thank you.
Yes, thank you for, I'll move on to the next slide, which just shows basically this public documentation that describes what I just showed you graphically on the previous slide. So the TSC value is the ART value times a ratio plus some offset. And I simplified things a little bit, but in the diagram, but this is the formal definition of invariant timekeeping is the section. All right, so as all of you know, synchronized time always comes from the outside. So we have CPU, and it was fine that we could measure the length of some code sequence within the CPU, but most of the interesting time synchronization problems are between systems. And so here, just as an example, we have some timing source. Maybe there could be multiple, but in this case, we have one. We have a network. We have a NIC. And the NIC in precision time protocol, at least IEEE 1588, and I recognize a few of your names from participation in IEEE. This is used then for timestamping, transmit, receive of certain event messages, maybe other messages. And in some cases, this counter is actually disciplined to match the time of the GM out there on the network. So let's just simplify it and say we have a representation in our system in the NIC of what time it is over right in the NIC. But of course, the software is running up on the CPU, and we have a TSC up there, timestamp counter, which is running independently, as we talked about. So really what we want to be able to do, and again, I'm sorry if this is going back to the basics too far, but I think it'll be instructive. What we really want is to be able to capture, as was just mentioned in the comment, we want to be able to capture the CPU time and some other time reference which we want to compare. And we want to do that as simultaneously as possible. And there's infrastructure in PTP4L with PHC to sys that allows a lot of this interaction to happen between the network time and the CPU time. And you definitely don't want to read the network time from the network controller when you want to know what time it is, because it'll take orders of magnitude longer to read this counter just like it would take orders of magnitude. I'm sorry, I'm pointing at the wrong screen. It would take orders of magnitude longer to read the NIC timer compared to the TSC, just like it would take orders of magnitude further to read the time source over on the other side of the LAN. What I'll do is I'll turn on my laser pointer, and then we can both be looking at the same screen. Okay, so if I subtract these two, and if the NIC counter is truly tracking the time source, then I get an error signal, which I can feed into some phase lock loop, PID controller, whatever, and therefore get the proper time through some linearity relationship between the CPU and the NIC. And so now let's go one more step back down into the software realm. So we have this timestamp counter. We talked about that, how it's derived from the crystal clock in a known way. And when I call clock get time with clock monotonic raw, what I get is nominal nanoseconds based on the free running, undisciplined, uncorrected TSC. So if my crystal that's driving, let's say it's a 25 megahertz crystal is driving my system, and that 25 megahertz crystal is off by 17 parts per million, then this number one will track the progression of time with an error of 17 parts per million, which is fine. It's just TSC scaled to nominal nanoseconds. If I want to find out what a duration of time is with respect to some external source, like if I'm running PTP or NTP, whatever, then I want to call clock monotonic, and then I get the TSC scaled to compensate for that 17 parts per million in my example of frequency error. And clock monotonic and clock real time gives me clock monotonic, but adjusted with the number of nanoseconds since 1970, for example, including leap seconds, typically, unless in some cases there are instances where people spread out a leap second over 24 hours, but ignoring that. So through the clock real time can have jumps in it forward typically. So going back to this, how do we know what the M is? So I think there was a presentation a few weeks ago on PHC, and this is an ioctal that will report the PTP time along with clock real time and monotonic raw for good measure. And it can do that in one of two ways. If the if the hardware is capable of simultaneously in hardware capturing the CPU time and the PTP time, then you can use the _precise version of this ioctal, and then you'll get a very, very precise pair. Yeah, very, very precise. If the hardware does not support the hardware cross timestamping, then the software will read the TSC, and then it reads down to the network clock, and then it reads the TSC, and you do some kind of ensemble, perhaps an average, in order to get that offset. Yeah.
Kevin, but this is a non-posted read from the NIC, right?
I'm sorry. Well, it's what from the NIC?
This ioctal is a non-posted read operation, PCI non-posted, which means that you need to do TLP to send the TLP transaction in the PCI and wait for the PCI to respond.
Yes, if you're doing a memory mapped read request to an Ethernet controller, for example, that's right. It's a non-posted. Yeah. It's yes.
So regardless of what is the NIC on the other side, that non-posted is at least 200 nanoseconds away.
Yes, so that was the point. That's exactly right. That was the point, that the counter in the NIC is far from the software.
Yeah. So I don't understand what the ioctal PHC what this line do.
So if you call PTP sys offset, then exactly what you said will happen. It will do a memory mapped read down to the over PCIe, for example, to the NIC, and it will read the TSC. Usually we'll bracket those reads with TSC so you can look for the smallest one, but you end up doing either having a lot of error or you end up doing a lot of reads or both.
Right. Yeah. Okay.
Now, if you have the ability to simultaneously capture this counter and that counter, then the underscore precise takes advantage of that capability.
But how this capability is even possible? Can you?
Okay, great. You are. I'm so glad that you joined because you're leading me exactly to the next slide. So there is a protocol that was defined by PCI, the PCI SIG, that allows a device, network device, to request the system time in a TLP, a special TLP. And so the idea is that if I call that PTP sys offset precise and the hardware can support PTM, then the driver would trigger a cross timestamp. This is just an example. A PTM exchange is conducted as shown on the bottom left. It's basically a sync delay request kind of transaction, but implemented over the PCIe link instead of obviously an Ethernet link. Very familiar, 4 timestamps are captured. Follow-up information is communicated in a following PTM response. So nothing new here.
Yeah, I think we also mentioned that in OCP Tech Week. This is great because we mentioned that the answer would be PTM. So
okay. Yes, so the PTM is designed exactly for this reason. Not only does it allow you to get this cross timestamp precisely, it eliminates a few memory mapped IO reads, but also you could imagine having maybe a NIC and some other device. Maybe it's a GPS, maybe it's another NIC, and implementing a boundary clock or transparent clock using the PTM as the method of sharing a clock. Because of course, boundary clocks in 1588 transparent clocks assume that you have a shared clock in order to do the RxTX timestamping properly. And PTM effectively gives you a shared clock across your PCI domain.
Does the CPU in those cases is always the master, or there are use cases where I'm sorry, the PTM master, or there are use cases where the CPU is not involved or it's the slave?
Yeah, we define PTM really to not be as flexible as 1588. So there's no BMCA. You can't adjust the port states, the port states for like you can in PTP. And so the requester, the endpoint is always the requester, and the root port is always the responder. If that makes sense.
And if it's a peer-to-peer, as you mentioned, like there is another IO device, the root has to be involved all the way.
Yeah, it's a northbound request always only, always northbound request, always a southbound response. And so then basically your system time becomes the common clock effectively that is used across your IO devices.
Got it. Thanks.
Yeah. Okay. Switch is also the timestamps are always communicated in units of nanoseconds. We decided at the time there was no need to talk about sub-nanoseconds like 1588 does. Who knows? Maybe that could be revisited in the future. And so switch effectively acts as a transparent clock. It could technically could also operate like a boundary clock, but those distinctions are not called out in the specification because they're not so relevant when we're talking about hardware kind of protocols like this. Okay, any questions, further questions from anyone else? All right, doing pretty well. I'm doing pretty well on time. Let me move to another one. So I've heard a lot of discussion about timestamp and time synchronization accuracy. So if we're going to achieve this idea of time synchronization that is accurate, more accurate than the best case communication latency, which is the requirement for the for causality, basically, then we need to talk pretty formally about the time stamping. If I'm running PTP4L, let's say, and on the screen it prints out the offsets, all I really know is that the offset that I'm measuring is changing. I really don't know anything about the absolute offset, because those numbers depend on the link being symmetrical. And in practice, it's never exactly symmetrical, although we can correct it to a large extent. So this is just a diagram I borrowed for today from a tutorial I gave to the IEEE 802.11 group years ago on time synchronization over Wi-Fi. I edited a couple of these things so it wasn't so Wi-Fi specific. By the way, 5G also has support for a profile of 1588, so it's similar there. But I have some round trip. Packets come down, packets come back. I assume that the round trip delay, each one-way delay is symmetrical with the other one-way delay. So if we're implementing PTP, then there is some point in the system where a transmit timestamp is captured. Let's call it, it's this horizontal line. And then there's some uncertainty, of course, and PHYs and barrel shifters and all the stuff that happens down below. And then it goes out into what is hopefully more or less a constant delay. Now, if it's in this case Wi-Fi, it is a single hop, and so we're only talking about electromagnetics, and so it's speed of light, but there's multipath, and so there's some variation in delay. If it's an Ethernet link and I'm running transparent clocks, peer-to-peer transparent clocks, then of course I have just a wire delay between stations, and I'm really talking about very constant delay because it's Cat5 in both directions. If it's a full network, then of course there could be substantial delays in either direction. But ignoring that for a minute, just looking at the system, on the other side, of course, there will be some timestamp point on the RX, some uncertainty. And then on the other direction, typically the timestamps are taken at different points, different numbers of nanoseconds from the RJ45 or the antenna for RX and TX. So there's some asymmetry in the timestamp point, even if it's implemented, when it's implemented in hardware, the timestamping. So we end up with this asymmetry. Good implementations always correct for any known asymmetry. And then there's also some uncertainty, which you hope is in the noise with respect to the total accuracy that you want to achieve. And you also hope that the uncertainty is distributed randomly in some way so that you can average over a long period of time and it goes away. But typically there's some fixed bias in the timestamp uncertainty that there's really no way of correcting using the protocol. If you're timestamping in the software application, then the uncertainty is substantially higher. Certainly there's asymmetry for receive versus transmit, delay asymmetry. If I'm not doing hardware timestamping, I'm only doing software timestamping, and I'm printing out what is the offset. And if I have a stable enough clock or temperature and I average over a very long period of time, then of course I can get an arbitrarily small number that is printed on the screen that is reporting the error signal, which can go to 0. But having an error signal going to 0 in without understanding and compensating for delay asymmetries is at least problematic, which is why the pulse per second output is so useful, which I'll talk about in a second. But just to close on this topic, so the instantaneous time error from station A to B or vice versa is equal to the instantaneous uncompensated delay asymmetry divided by 2. And if I do a long-term average, of course, I get the average delay asymmetry divided by 2. Math error there. So there's a divided by 2. You don't get to cheat physics by having a long-term average. And the point there is that if there are offsets that are not random, then averaging isn't going to help me long term. So what we like to do then is use a pulse per second, let's say, out of the NIC, driven by the NIC clock, which then allows us on an oscilloscope to, this is really the proof of the accuracy. And I think it's great to look at the PTP4L output on the screen, but the proof is really at the physics if we're talking about causality. And I think probably, and this is a known technique within the timing world to use pulse per second, and a lot of devices these days support those. Any?
So Kevin, sorry.
Please.
Just a quick feedback from OCP Tech Week. We actually support the fact that those things need to be accurately measured, and we actually demonstrated together. The OCP team demonstrated a way to do it in scale, even without a scope. So we are fully supported with this claim. I'm trying to understand what's the point behind the delay asymmetry weak point, as we know exists both on PTP and also on PTM, and actually there are ways to overcome them, but all the ways are outside of the protocol, as you accurately mentioned.
So if we're doing pulse per second, I guess this was leading me to the pulse per second. Once we do pulse per second, now we really know, because we have an edge, we can measure it. And if this clock is used for generating the pulse, and that one as well, then all of these uncertainties are already included in that measurement, and we're good. I guess the other, the point I wanted to make is, and again, maybe it's, everyone is far beyond this, but to see a offset in PTP4L, for example, go on the screen, those offsets do not know about these uncertainty, they don't know about any bias in delay asymmetry, nor about any fixed propagation delay asymmetry across the network. And so those are only measurable if you really get to the, for example, pulse per second type of measurement.
Yes, as you mentioned, the PTP4L printouts and any PTP daemon printouts is doing long-term averaging.
Yes, and if I have a sufficiently stable reference clock in my GM and in my end station, and if I do averaging over a long enough period of time, then even though the error could be a millisecond because of delay asymmetry, on the screen it will say 0 nanoseconds. Eventually I can get to 0 nanoseconds if I have a sufficiently stable crystal and I average over a long enough period of time. But in the statistics of the network will behave, which typically they are over infinite time. So that was my main point, is that the accuracy that we report, it matters a lot. It matters a lot if it's a software estimate of the error, which is really just the jitter, or if it's the real hardware measurement.
Yeah, but you know that it goes vice versa as well. Sometimes the PTP4L can give you much worse result than the actual physical measurement. For example, we always care about the difference between our ordinary clocks, and the PTP4L give us the phase between the ordinary clock and its own master. And sometimes if the phase is correlated properly, it could be less noise between the ordinary clock.
Yes. Yep. Good point. And having multiple PTP GMs simultaneously is one thing that I know a number of industries are looking at. Also for improved robustness, but certainly the accuracy is better. You can imagine, I guess, in the extreme, and there have been examples of this implemented outside of PTP, where every device is sending it, every other device, its notion of what time it is, and some amount short of that, I think, could be useful. Okay, a couple other.
Kevin,
go ahead. Yes.
One quick question. By the way, it's nice to see you.
Michelle?
Yeah, Michelle. Yeah.
Hey, Michelle. Great to hear from you.
There was a lot of work done in the late 2000s within IEEE in a group called 802.3BF, which was trying to address a bit the point that you just mentioned in the previous slide, with all of these various sources of errors, specifically the asymmetry between the TX and RX. It seems that the PHY community never really picked up on that, and never really, today, even if I look at a PHY, rarely will I see, these kind of numbers provided by the PHY manufacturer. And that was the intent of that piece of work in .3BF, was to make sure that the PHY vendors could advertise, those sources of errors and their magnitude. Any comment on that?
Yeah, it's a great point, Michelle. Maybe this group could have an impact on that. Maybe that could be one of the topics to discuss, about getting some standardization of reporting of delay asymmetry, or even absolute RX delay and absolute TX delay. That would be fine too. But and also the delay is typically in modern PHYs is not a fixed number. It can change from link up to link up. And so there's also a software component there where it's important to be able to report at runtime what is the delay, and then be able to propagate that up through the software stack if it changes, during operation. Typically not during operation of the link. You link down, you link up. Okay, now you're going to somehow reset your PTP protocol, but being able to report that. So yeah, I agree that this is an important thing for drivers to know about their hardware and to be able to report, whether they're static or reported at runtime or link up. Especially when we get down into the lower accuracy, better and better accuracies. It's more and more important. Any other topics or questions before I continue?
So while this is Alon Regev from Keysight, so while we're talking, hi Kevin, how are you doing? So while we're talking, there is, by the way, another 802.3 group that's meeting right now that's talking about specifically where to timestamp packets and how to pass that up the stack again. So that topic hasn't gone away from 802.3 either. As a comment.
Yeah, and there's the standardization, and then there's the actual productization and deployment, I guess. So I don't think we don't need a new standard in order to improve the reporting of what is the delay symmetry. I mean, this is pretty straightforward to talk about what is the thing that we want reported, and then making it possible to expose that up the stack. But it does end up being a bit like a chicken and egg problem sometimes. But it's good to know along that the .3 is continuing to work in this area. Okay, I wanted to just mention virtual time, just as a, it's important to be able to think also about, what do I do if I have a number of VMs and if they are accessing the same PTP time? And there are a few approaches to this. I think there was some presentation that Chris, who's on the call, and I put together a couple of years ago, maybe it was ITSF, on virtualized time and multiple models for doing that. But regardless of how it gets implemented, whether it's the host OS or hypervisor that implements PTP and then just publishes the coefficients, or if there's some kind of open vSwitch for PTP or support for that that causes then each VM to have to run its own PTP instance, I guess is a design decision. But there is this question about virtual time versus physical time on a virtualized machine. And I don't want to, there's not a huge amount we need to talk about it today, but just to say that there are cases where you don't want an application to realize that it's virtualized. And in that case, you would provide some kind of virtual time that is not tied exactly to even TAI. And that can cause problems with some kinds of applications that are using time for something other than performance measurements and coordination among a small group of other clustered devices.
Hi, Kevin.
Yeah.
Elad here, NVIDIA. So a quick question here that we've been getting often is, what is the support that Intel has today for PTM?
Yeah.
So when can we get devices or platforms that will allow us to have that fully tested?
Yeah. So I'm not here to talk about products. I never do.
Right.
So really today it's just about the technology, some of the history, some of the technology that is available in the standards. Yeah. So I guess there are even public things that I could talk about, but I just send you to Google or let's talk offline.
Because this is very helpful.
To a product discussion. Yeah,
understood.
It's a great question, and PTM is, I think, it is very important, and it'll allow better access to time and to software applications. Although today, PTP time is accurately available to Ethernet controllers and hardware devices just through the TPS types of interfaces.
Right. Understood. Thank you.
Yeah, absolutely. So getting back to the kind of the big idea here of this time singularity, where if time is known to be better, time between me and you, our synchronized time is known to be better synchronized than the best case communication latency, that gives us the limit of causality, and we can use time as a criteria for the correctness of an algorithm, not just for the better performance, not this continuum of performance, but actually a binary correct incorrect. And this is a hard problem, because to do this at scale, it requires that we can actually know with very high certainty what the worst case inaccuracy is. The best case communication latency is perhaps easier to calculate with a meter stick because of the speed of light. But certainly it's possible to achieve better accuracy than what you would see as a delay of speed of light. Obviously, that's been achieved in many places, including GPS. But this is an interesting challenge, I think, for the industry, is how to deploy the technology at scale that allows this time accuracy singularity, as I call it. And then you can do, if you think about correctness of an algorithm, you can also think about safety systems and real-time systems, as well as distributed applications. And hopefully the video comes through. But the idea is once the devices are synchronized, then I meant to mute this.
Kevin, we actually, may I suggest, we are using the opposite terms.
I'm sorry.
We assume that we will never be.
Hang on just a second. Sorry, what was that?
I was saying that I'm suggesting to adapt what we started here as I would say opposite term, since we know that there is no such thing in a digital world as purely accurate. Then what we defined is the opposite term as what is the error bound? How distant are you from any other device in your system? That's the terminology that we use, and
Yes. Yeah, great point. So if the error bound is useful in some cases. In other cases, all you need to know is the worst case. But if you know the error bound, then by definition, you also know the worst case. So I think, yes, the error bound is definitely sufficient. But what is the best case? Obviously, the best case is 0 nanoseconds error. What is the worst case is the more challenging question.
You know that CERNs go below nanoseconds. There is no 0 here. It will be pico, and then I don't remember the next scale after pico.
Femto, I think.
Yeah.
Yes, as far as what would be able to be demonstrated. But I think typically, if you know the worst case, it's enough. I don't need to know what the best case accuracy that could be achieved is, as long as I know the maximum. But absolutely, the knowing the error bound and how much jitter there is, let's call it, in the time accuracy, can allow optimization of other system level characteristics of the system. Okay, so I'm on my last slide now. Just really the summary is it's a big challenge to think about a plurality of nows that can be trusted, and where, okay, worst case accuracy, where the worst case error bounds of accuracy with respect to a source that is quantified and is known for sure. And the singularity really is worst case accuracy better than the best case network latency. And for distributed software applications, having immediate access to that time is obviously that's the panacea. That's what we're trying to get to in the timing community. Okay, other questions, comments? I guess we have about 1 minute.
This is a good background and summary. Thank you, Kevin. I think we at TAP here have been dealing with implementing, in fact, these principles. So appreciate that background you just shared. It would be interesting to see how we can leverage the CPU complex to reach greater accuracies.
Okay, anything else? If not, thanks for the time, no pun intended, and look forward to the continued progress this team will make.
Kevin, thank you so much.
Thanks, Kevin. Yeah,
Thank you, Kevin. Thank you.
Kevin. Thank you. Great talk.
really good.
Thank you. Bye.
Bye.